Hello, Mr. Claudia here, and today we have our final lesson in the probability chapter, and we're going to be learning another tool that we can use to solve probability problems. It is probability tree diagrams. So, first of all, a tree diagram is just another way to lay out all possibilities in a probability problem. Remember, we've already learned some other ways to lay out possibilities, such as a sample space diagram, Venn diagram. Now we have probability tree. They work best with multiple events. So actually, you'll find that this lesson really helps put the last two lessons on conditional and independent events into context. So there are two types of problems we're going to look at. We're going to do two examples today. The first one is a probability tree with replacement, and another one without replacement. If you remember from the last few lessons, this one would be with replacement is independent events, and this one here without replacement would be dependent events. Okay, so let's get started with our first example, which is independent events. So the probability that Andre Drummond of the Detroit Pistons successfully sinks a free throw, this is in basketball, so a free throw is when you take a shot from the foul line. The probability that he successfully sinks a free throw is 0.39. Assume that Andre's free throw shots are independent of each other. If he takes 3 free throw shots, what is the probability of all these things? He is successful 3 times in a row. So first of all, let's just think for a little second. So Andre Drummond is a professional basketball player. He gets paid a lot of money to play basketball. When he goes up to the foul line, which is not really that far from the basket, and he shoots, he successfully sinks the shot less than half the time, almost 1 in 3, right? The almost like 0.39%. This is pretty terrible. I mean, Andre Drummond is a little famous because he's actually the worst, or one of the worst, free throw shooters in the NBA. For a while there, he kind of improved the stat, and now he's back at the bottom. So, I mean, can you imagine being paid millions of dollars and you can't even really do your job properly? Such an interesting thing. Okay, so what we're going to do is we're going to draw a tree. He's taking 3 shots, so I'm going to draw a tree to depict all the different things that can happen. So let's start midway down the page here. So first of all, the first shot. Okay, so there's 2 options for the first shot. He can either score or he can miss. What's the probability that he scores? 0.39. What's the probability that he misses? Well, it's 1 minus, it would be the other half of this, right? 1 minus 0.39, which is 0.61. So see how I've labeled the two outcomes, and then the probability is on is written on the leg here. Now that is just the first shot. Okay, what about the second shot? Well, okay, let's say he scores the first time. Then I'm going to draw the 2 outcomes for the next shot. Again, we have score and we have miss. Or he could have missed on the first shot, and then he could shoot again and he could score or miss. So that is the second shot. That's the way things can go. We can keep doing this, right? Because he's taking 3 shots. So on the final shot, well, look at all the different possibilities we have now. So we have score, miss, score, miss, score, miss, score, miss. And that's the third shot. So that's, you can see there's a lot of possibilities for these 3 shots. You can score, 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 miss, score, miss, score, etc., etc. Now, notice that it said that the free throw shots are all independent of each other. That means the probability of him scoring the second shot it's independent of whether he got the first shot in or not. So the probability doesn't change. So throughout the entire tree, the probabilities of scoring and missing are always the same. It's good that the question explicitly told us this, because it might not be true, right? If Andre Drummond misses the first shot, it might get in his head and make him more likely to miss the next shot. So maybe these aren't independent, but it's been told to us in the question that they are. So we now can label all of the branches of my tree. Okay, so we're just going to make a note of that. So here, this would be the probability of missing. And here is the probability of missing given that you already missed. And you can see it's the same as just the probability of missing. So we'll just make a little note for independent events. The probability does not change due to earlier events. And that's no surprise, we've already looked at that. But just so you understand how the tree works. Okay, now let's do part A, question A. So what's the probability that he is successful 3 times in a row? So the probability of a success, then a success, and then a success. Or score, rather. So that would be, based on our lesson about independent events, I would just multiply these 3 probabilities. 0.39 times 0.39 times 0.39. Or 0.39 to the power of 3, which gives me 0.0593. Remember, 3 significant figs. The leading 0 does never count. So 0 to the left never counts. Now, if you want to look at that on the tree, you could have seen that right here, right? Score, you multiply these 3 probabilities together. Okay, question B. What is the probability that he is successful only once? So look at our tree. Can you trace out some different possibilities where he's successful only once? Well, he could score, where's my other colored pen? I guess I'll just use this, orange. So he could score, miss. That would be one possibility, right? In that scenario, he is successful only once. So for part B, that would be the probability of score, miss. So that would be a probability of 0.39 times 0.61 times 0.61. And I get 0.145. Okay, but I'm not done yet, right? Because that's just the probability that he got the success on the score on the first shot. He could have also, another option would be if he had missed the first shot, scored the second shot, missed the third shot. Well, the probability of that happening, that's the probability of miss, score, miss, is 0.61 times 0.39 times 0.61. It's actually the same as 0.145. But I'm not done, because there's another possibility. He could have missed, score. So see how the tree helps me lay out all of the different things that can happen. This is the same probability, it's 0.145. Okay. Now, we are going to look, we have 3 paths. We know the probability of each of them. Remember, the probability of all of these paths adding up, it should add up to 100%. These are all the different options. Now, for him to score only once, we have to add up these 3. So, since these 3 paths are mutually exclusive, we add the three probabilities. And 0.145 plus 0.145 plus 0.145, this gives me 0.435. So the probability that he's going to get one basket in is still less than 50%. So that's not so great. For our final question, we want to know what is the probability that he is successful at least once. Where is that? At least once. So think about what this means. That could mean score, 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 miss, score, miss, score. A lot of options, right? Because really, to score at least once means you can score once, twice, or 3 times. So what you would have to do for this one, if you can imagine, you would have to add up the probabilities of 7 paths. Right? All 7 of these paths. The only path you wouldn't add up would be miss, miss, miss. But it might be easier, instead of doing this, is to use the complement. So instead of adding up 7 paths, you would just take 1 minus the probability of missing 3 times. So that would be 1 minus 0.61 times 0.61 times 0.61. Oops, sorry. The probability of scoring, of missing every time, which is this leg here, 0.61 times 0.61 times 0.61. That gives me 0.61 to the power of 3, 1 minus that answer. That gives me 0.773. So he does have a 77% chance of sinking 1 shot out of those 3. So it's a little bit better. Either way, you can see how the tree is useful to help present the data and then to develop a solution. Especially like for something like this last one, it might be hard to come up with this without seeing it. Okay, let's turn the page. Now this example is for dependent events, and again, I don't like that it's just drawing marbles from a bag. Like, couldn't we do something more interesting and more powerful? But this example is very, very common. These kind of questions are very common in IB exams, so it is good for you to see a question involving bags of marbles, because obviously everybody uses bags of marbles very frequently. So you have a bag with 2 purple and 5 green marbles. Marble is drawn from the bag. Now you take the marble out and you don't put the marble back, and then you draw a second marble. So this is the key thing, right? Without replacement, without putting it back. That means that this is dependent events or conditional probability. Yeah, as you'll see as we draw the tree. So let's start. The first marble is drawn. So you draw a marble. Now you can either draw purple or green. This is my first draw. What's the probability of drawing purple? Well, there were 2 out of 7 which are purple and 5 out of 7 which are green. Now after the first draw, you draw again. So you can either draw purple this time or green. Purple or green. And that's our second draw. What are the probabilities here? Well, look, remember, I threw the marble away. I didn't put it back in the bag. So let's say I drew purple. After the first purple has been drawn, there's only now 1 purple left in the bag, and there are only 6 balls left in the bag. So my probability has changed. What about green? Well, there's 6 balls left in the bag, but there's still 5 green. Down here, if I draw a green the first time, and then there's still 2 purple, but there's only 6 options. And here, if I draw green the first time, now there's only 4 green left, and there's 6 options. So you can see that the probability of every branch of my tree has changed based on what happened in the first draw. If you want to call this the probability of green, this would be the probability of green given that green has been drawn. This one here would be the probability of purple given that green is drawn. So just to give you kind of an idea, probability of green given purple, and this is probability of purple given purple. So just to show how they still relate to the conditional probability lesson. I'm just going to make a quick note here like we did last time. Note how the probability for the second event changes based on the first event. And that is dependent events, or conditional probability. Okay, so now the question, now that I have my tree, the question, I can use the tree to analyze my question. Determine the probability that the two marbles are different colors. Well, let's go through my tree and trace out these two options. Purple, purple, the same color. So it would be purple, green, or green, purple. Those are my two possibilities. So now I use the tree to figure out that probability. So it would be purple, green. The probability of that is 2 over 7 times 5 over 6. And then just like in the last question, I add that to the other branch probability, which is 5 over 7 times 2 over 6. This gives me 10 over 42 plus 10 over 42, so I end up with 20 over 42. That is how you use trees, probability trees, to solve probability problems. And you're going to find that even though this is the last lesson in the chapter, this strategy is employed by many questions that you might see in an IB exam, because really this strategy uses almost all the things we've learned in the past little while. Independent events, conditional probability, even finding theoretical probabilities is in here. So these questions are very common. Your homework is page 90, number 1 to 6, and page 92, number 1 to 6. Good luck with that, and we'll see you next time.